in previous class I taught you about three types of configuration in BJT transistor, that is common emitter, common base and common collector. Okay. Now in this class I will teach you about biasing. Okay. Transistor biasing. Okay. So a common emitter BJT transistor, this is generally used for amplification purpose, because a BJT in common emitter mode, it has high voltage gain, high current gain, high power gain and output resistance to input resistance, it is sufficient high. So because of these reasons we are generally using common emitter mode BJT transistor in an amplifier circuit. Okay. So suppose this is common emitter mode NPN transistor. This is RC and this is VCC, this is VDD and this is base terminal, this is collector terminal and this is emitter terminal, and this is the V input, AC input that we want to amplify. Okay, and this is the resistor across which we will get V out. Okay, and since this is in common emitter configuration, so its current amplification factor is beta. Okay, so for this type of circuit, this is an amplifier circuit. Okay, in common emitter mode by using common emitter mode BJT transistor. Okay, now if we will see the operating point. Okay, so in order to determine the operating point of this BJT, so we have to determine its Q point or quiescent point. Okay, Q point or operating point. How it can be determined? Okay, we are determining the operating point or Q point of this transistor. That is, what is Q point or operating point? It is the value of IC and value of VCE when Vin is 0. That is, under this case, when Vin is 0, then what will be the value of IC and VCE? This determines the Q point. Generally, the operating point should lie in the middle of the active region. Okay, on this DC load line. This is, say, DC load line. Okay, so the output characteristics is like this. Suppose this is VCE versus IC, and this saturation current IC, it is equal to VCC by RC, and this is VCC, this point is VCC, and the output characteristic curve, it is like this. Say IB, it is equal to 0 microampere, like this. Suppose here IB, it is equal to, say, 4 microampere, IB, it is equal to, say, 8 microampere, and it is 12 microampere, it is 16 microampere. IB, it is equal to 16 microampere. Okay, So this is the output characteristic curve of a common emitter transistor. Okay. So output characteristic curve, it is the graph between IC versus VCE for different values of IB. Okay. So for any amplifier circuit, first of all we have to determine the Q point or operating point. So Q point, it should generally lie in the middle of the active region. This is cut off region and this is saturation region. And this is your active region. Okay. Now in general, the Q point, that is the operating point under Q point, that is IC and VCE, value of IC and VCE under no signal, means when Vin is equal to 0. Okay, so only VBB and VCC, only DC voltages are present. Then in that case, what is the value of IC and what is the value of VCE, it determines the operating point. Okay, so operating point should lie in the middle of the active region. Okay. So this is VCE, this is IC. First of all, we have to draw the load line. How we can draw the load line? This is VCC and this is VCC by RC. The circuit is like this. For what circuit? Circuit is the same. This is VCC and this is VBB and this is Vin and this is base terminal, emitter terminal and collector terminal. Okay, and this is RC. V output we are taking across RC. So just now I told you that in order to analyze the amplifier circuit, first of all we have to determine the Q point. And Q point or operating point, we have to fix the operating point in the center of the active region and on this load line. Okay, so this is say point A. Suppose another operating point which is B and this is another operating point which is C, and the output characteristic of it is like this. Okay. Suppose this is IB, it is equal to 0 microampere. IB, it is equal to say 4 microampere. Here it is 8 microampere. Like this, increasing. Okay. Now, suppose there are 3 operating points. We are choosing 3 operating points: A, B, and C. So, A, B, and C. Okay. This operating point A, it is in the middle of active region. Okay, and C is near to the cutoff region. This is cutoff region, and B is near to the saturation region. then what will happen to the output signal? If the operating point is at A, if the operating point is at B, if the operating point is at C. Okay? So if the operating point is at A, then the amplifier will amplify the input signal well. Okay? So amplification is faithful. Amplification of the signal is faithful when the operating point is fixed at the middle of the active region. Okay? Now, if the operating point, so if the operating point is at A, then the input signal, it will be amplified faithfully. Okay? Now, if operating point is at B, near to saturation region, then what will happen? Then suppose input signal is like this. Suppose this is V in. This is V in. Okay? So if operating point is at B, then some of the positive half, it may be clipped in the output. It will be amplified, but some of the, after amplification, some of the positive half of the input, it may be clipped. Okay, because the operating point is near to the saturation region. Now, if the operating point is near to the cutoff region, then what will happen? Then some of the negative part of the signal. Suppose this is negative half, so some of the negative half of the signal, it will be clipped. So amplification, it is not faithful in both the cases. For if the operating point is at B, if the operating point is at C, then the amplification is not faithful. We will not get the complete amplified signal. Okay? So amplification is faithful only when the operating point Q, if it is fixed on the load line in the middle of the active region. Okay? So this is the importance of operating point. So we have studied the importance of operating point. So operating point or Q point, this is without the input signal, without this input signal. So it is due to the biasing voltage. Okay? So first we have to fix the operating point in the middle of the active region. Okay? How this is fixed? This is fixed by this biasing voltage. Okay? So biasing voltage is needed to fix the operating point. Okay? In the middle of this active region. So once this operating point is fixed, then if we are applying the input signal, then a good amplifier, it for the complete signal, that is for this plus half and minus half. Okay, this operating point, it should not go to the cutoff region or it should not go to the saturation region for the complete input signal. Okay, because if this operating point, that is if we are applying the signal, that if the signal is applied, then the instantaneous Q point, it will move. Okay, so its maximum limit, it should not go below the cutoff point and above the saturation point. It should lie, that is Q point should lie in the active region for faithful amplification. So biasing is required. Then after biasing, so biasing is required in order to fix the operating point in the middle of the active region. So once the Q point is fixed, then we have to see that this Q point, it should not change with the variation in temperature. Okay, so IC, it is equal to, in case of common emitter configuration, IC, it is equal to beta times IB plus ICEO. So it is also written like this: beta IB plus beta plus 1 into ICBO. Okay, so IC, we can write IC, it is equal to beta IB plus beta plus 1 into ICBO. Okay, now from this expression we are saying that IC depends on beta, IB and ICBO, and all these terms are temperature dependent. Okay, that is why we have to use stabilization. Stabilization of the Q point. Okay, so we need for stabilization of Q point. Why we need stabilization of Q point? Because IC expression of IC, it is equal to beta IB plus beta plus 1 into ICBO. So we can see the expression. From this expression we can see beta, it is temperature dependent, IB, it is also temperature dependent, and IB or BBE and ICBO, it is also temperature dependent. Okay, now with the increase in temperature, if temperature increases, then beta, it also increases. Okay, and so with the increase in temperature, beta increases. Then ICBO, it doubles. Generally the value of ICBO, it doubles with the increase in approximately 10 degrees centigrade rise in temperature. So if temperature increases by 10 degrees centigrade, then ICBO, it approximately doubles. Okay, that is, so we can say that IC, it also depends on temperature. Then third parameter, it is VBE. Okay, now VBE, its value, it decreases by 2.5 millivolt per degree centigrade. Okay, so IC depends on temperature. Okay, that is why we have to use, we need stabilization. Okay, after fixing the Q point, in the middle of the active region, then this Q point, it should not change with the variation in temperature. Okay, so we have to think it should not change with the change in transistor. And third, it should not change due to thermal runaway. Okay, that is why stabilization of Q point is essential. Okay, so IC. Okay, so we have just discussed how IC is dependent on temperature. So IC is dependent on beta, IB, IB in turn VBE and ICBO. Okay, so these three parameters are dependent on temperature. So IC is also dependent on temperature. That is why we need stabilization of Q point. Okay, so we need biasing circuit to fix the Q point. Okay, so second is change in transistor. Okay, if this transistor is say faulty, then if we replace another transistor with the same type, then beta will differ. Okay, suppose this transistor is faulty, one transistor is faulty, and we are replacing this transistor with another one of the same family, then beta will differ. So if beta will differ, then definitely operating point it will change. Okay, so because of this operating point also changes. Okay, then due to thermal runaway, see the expression for IC, it is equal to beta IB plus beta plus 1 ICBO. Okay, now with the increase in temperature, if temperature increases, then ICBO it increases. So if ICBO increases, okay, then this will again increase IC, the value of IC. Now again, if IC increases, then power dissipation will increase. Again, if power dissipation will increase, then this will increase the temperature. Then again, due to the increase in temperature, ICBO will again increase. So this will go on. So this process it is known as thermal runaway. So because of this cumulative effect, temperature rises very high and this will destroy the transistor. Okay, so these are the factors due to which we need biasing circuit, we need stabilization circuit. Okay, so because of these three reasons we need biasing circuit. So biasing circuit is required due to these reasons. So biasing circuit, okay, why biasing circuit is required? Biasing circuit is required first to fix the Q point in the middle of the active region, and second, this Q point it should not change due to the variation in temperature, due to the change in transistor and due to thermal runaway. Okay, so we are using the biasing circuit for stabilizing the Q point in the active region. So with the change in temperature also, this Q point it will lie in the active region. With the change in transistor, again beta will change. So if beta will change, but by using the biasing circuit, again it will not affect too much in IC. Okay, then with the thermal runaway also this should not change. Okay, so biasing circuit is required. Okay, we will study about stability factor. Okay, so what is stability factor? It is denoted by S. Okay, so stability factor of any amplifier circuit in ideal case S is equal to 1. So lower will be the stability factor, better will be the stabilization of the Q point. Okay, so in case of common emitter configuration, IC it is equal to beta times IB plus beta plus 1 into ICBO. We can write like this expression for IC. Okay, now stability factor it determines the change of IC. It determines the fluctuation of IC, okay, with the variation in temperature, with the variation in beta, with the variation in VBE. Okay. Now, so stability factor, it is equal to del IC divided by del ICBO when beta and IB, or we can write VBE, it is constant. Okay. Or we can express stability factor another way. It is S beta, it is equal to del IC divided by del beta when ICBO and VBE, or IB, it is equal to constant. The expression for IC, it is equal to beta IB plus beta plus 1 into ICBO. Okay. So again SB, it is equal to del IC divided by del VBE when beta and ICBO is constant. So first stability factor we are defining like this, as it is equal to del IC divided by del ICBO when beta and VBE or IB are constant. Okay. Now stability factor in terms of beta, it is equal to del IC divided by del beta when ICBO and VBE are constant. Okay. And another stability factor, it is S in terms of voltage V, it is equal to del IC divided by del VBE when ICBO and beta both are constant. Okay. Okay. So we are saying that stability factor, it is the rate of change of collector current with respect to the leakage current ICBO when beta and VBE both are constant. Okay. Now stability factor S beta, it is equal to change of collector current with respect to beta when ICBO and VBE are constant. Okay. Now SV, it is equal to del IC by del VBE when ICBO and beta are constant. Okay. So we will study the stability factor based on the variation of ICBO. Okay, that is rate of change of IC with respect to change of ICBO when beta and VBE are constant. Okay. So from this expression, it is clear that S, it is equal to unity for idle case. Okay. So the stability factor in idle case, it should be 1 for idle case. Okay. But in practice or in practical case, S is not equal to 1. So if S is less than 25 also, then we can say that the amplifier is faithful. Okay. So amplification is faithful. So for faithful amplification, the stability factor, it should be low. So if the stability factor, if it is low, then the stability of operating point it is high. Okay. If the stability factor is low, then the stability of operating point with the variation in temperature, with the variation in VBE, with the variation in ICBO, it is high. Okay. So we have to design the Basel circuit such that the stability factor it should be low. Okay. So that the stability of the operating point it should be high. Now we will determine the stability factor. Okay, so IC we have written IC it is equal to beta IB plus beta plus 1 into ICBO. Okay, this is the general expression for IC in case of common emitter configuration when the BJT is in common emitter configuration. Okay. Now we know that stability factor as it is equal to del IC by del ICBO. Okay. When beta and VBE are constant. Okay. Now we can write this equation like this: del IC it is equal to beta del IB plus beta plus 1 into del ICBO. We can write like this. Okay. So again we can differentiate this equation with respect to del IC. So it is equal to this beta del IB divided by del IC plus beta plus 1 del ICBO divided by del IC. Okay. Now this is equal to 1 beta del IB divided by del IC plus beta plus 1 del ICBO by del IC. S is equal to del IC divided by del ICBO. So it is equal to S. Okay. So we can write this equation we can write like this: beta plus 1 divided by S it is equal to 1 minus beta into del IB by del IC. Okay. Now we can write the stability factor. How we can write down the stability factor? It is equal to stability factor. It is equal to 1 plus beta divided by 1 minus beta into del IB by del IC. Okay. So this is the expression of stability factor of BJT in common emitter mode configuration. Okay. So we can write down the expression for stability factor like this, where S is the stability factor. Okay. For ideal case, stability factor it should be equal to 1. Okay. But practical, this is not practical. Okay. So in practical, S is more than 1. Okay. So if S is below 25, then we can say that the amplification is faithful. Okay. So we have studied about the stability factor. Okay. So what are the requirements of biasing circuit? what are the different requirements of biasing circuits. Okay, the first requirement is that we should choose the operating point in the middle of the active region. Okay, so the biasing circuit, first it should be designed in such a way that the operating point should lie in the middle of the active region. Okay, suppose this is the operating point. Okay, and if this is VCE versus IC. Okay, this is say IB1, IB2, like this, and suppose this is IB5, this is IB4, this is IB3. Okay, and this is saturation region, this is active region. Suppose IB1 it is 0 microampere, so below this it is cutoff region. Okay, now the biasing circuit should be designed in such a way that the Q point, that is operating point, should lie in the middle of the active region. Okay, so this is under no signal condition. Now once the signal is given to the biasing circuit, then this operating point it should not go to the cutoff region, or it should not go to the saturation region even at the extreme values of the input signal. Okay, so this is the first requirement, is that to fix the operating point by designing the biasing circuit in such a way that the operating point should lie in the middle of the active region, and after applying the input signal it should not go to the cutoff region, or it should not go to the saturation region even at the extreme values of the input. Okay, so this is first requirement, and the second requirement is that this Q point, instantaneous Q point, it should not change with the variation in temperature. Third requirement is that the operating point, that is IC and VCE, its value should not change with the change of the transistor of the same family. Okay, suppose one transistor, there are two transistors 1 and 2, both the transistors are of the same family. Suppose this transistor is in the circuit, but after failure of this transistor, suppose we want to replace this one transistor with two of the same family. Okay, so the operating point, this operating point, it should not change by replacing this transistor with the another transistor of the same family. Okay, so these are the main requirements of biasing circuit. Now we will see the effect on operating point. Suppose the circuit is like this. This is RC This is VCC. This is VBB, IB. This is IC. This is IE. Okay. This is V in and V output we are measuring across RC. This is the simple amplifier circuit in common emitter configuration of BJT. Okay. Now, if you want to draw the load line for this circuit, how we can draw the load line? It is VCE versus IC. Load line at this point it is VCC, at this point it is VCC by RC. Okay, so we can draw the load line for this circuit. This point is VCC and this point is VCC by RC. So this is IC saturation. Okay. Now the output characteristics is like this. Suppose this is IB1, IB2, IB3, IB4. Suppose this is IB5. Okay. Now we will see the effect on variation of IB. What will be the effect on variation of IB on the Q point? Okay. Suppose this is Q1, this is Q1, Q2, Q3, Q4 and this is Q5. Okay. Now from this output characteristic curve we are seeing that with the increase in IB, operating point shifts upward like this way. IB, if it increases like this, IB1, IB2, IB3, IB4, okay. So Q point it increases in this manner. Okay. So this is the effect of IB on Q point. Then we will study the effect of variation of VCC. Again this is VCE versus IC and this is load line VCC by RC versus this is VCC point and like this. Suppose this is IB1, IB2, IB3 and IB4. Okay. Now it is VCC1 divided by RC. Okay. Now suppose VCC1 it is more than VCC2 like this. If VCC1 is more than VCC2 more than VCC3 like this. If we are applying 3 VCC, VCC1, VCC2 and VCC3, then we will study the effect of variation of VCC on the Q point. Okay. So this is VCC1 divided by RC. Then second plot it will be like this. The same VCC point it is VCC1 divided by RC, VCC2 divided by RC. Then third line it will be VCC3 divided by RC, where VCC1 is more than VCC2 and VCC2 is more than VCC3. Okay. So now we are saying, suppose for a particular IB2, okay, we are observing the Q point. So this is Q1, this is Q2, and this is Q3. So we are seeing the effect of variation of VCC on Q point. So this is the effect. This is the variation of Q point. This is the variation of Q point because of change in VCC. Then we will see the effect of variation of RC on Q point. Suppose RC1, RC2 and RC3. These are the three different values of RC. Okay, so it is VCC by RC1, VCC divided by RC2 and VCC divided by RC3. These are the three values of saturation current. Okay. Now, if this is high, then this term will be less. Okay. So, if this is low, okay. So, we can say that if this is the relationship and this is VCC by RC1, VCC by RC2 and this point is VCC by RC3. Okay, where RC1 is less than RC2, which is less than RC3. Okay, then again we will get 3 points. This is Q1, Q2, Q3, and the variation of Q point, it will again will vary like this. This is Q1, this is Q2 and this is Q3, and for a particular value of say IB2. Okay, so in this manner Q point varies with the variation of IC.